Welcome, everyone. Good to have you back again. So, today we are going to continue our conversation about the power of compounding. I'm going to do two things. One is I'm going to differentiate between the discrete case and the continuous case. And second, given any of four of the letters or parameters, can I solve for the fifth one? So you may remember last time we built this formula from scratch. Future value equals present value times 1 plus the rate of return per annum. This is always annual over n. N is how often you compound, and t is time in years. And you notice there are five parameters. And given any four, can you solve for the fifth? The answer is yes, with one exception. Notice n shows up twice. So I will never be able to solve for n. For example, if I say to you, you have $1,000 now, which is going to triple to $3,000 later after 10 years at a rate of 6%, how often were you compounding? I'm not going to be able to do that. If you try to isolate this n, you're going to trap this n even more. If you try to isolate this n, you're going to trap this n. So, and you can never combine these n's. So we will never solve for n, okay? The easy one to solve for is FV, because FV is written explicitly in terms of the others, like I did before. Just dump those four numbers and you get the answer. Before I continue to how to solve for PV or R or T, let me show you the continuous case. So N is how often you compound. What if I want to compound continuously? Continuously, at every split second. All it means is you take your expression, the discrete case, and you force n to go to infinity. So basically you take a limit as n goes to infinity of the discrete case. To make the story short, after, I don't know, 4, 5, 6 lines of calculus BC, you're going to end up with this formula, which I'm not going to prove for this course. It's beyond the course. But what happens is, for those of you who took BC, not AB, you maneuver the letters and you create some dummy variables, and you're going to encounter a very famous limit in calculus, and that's where the E comes from, right? E is just a number. And you come up with a really nice, simple formula, okay? Notice it only has four parameters, not five, which is even nicer. So it's actually easier to work with this than to work with this. So to solve for FV, well, it's right there. You just plug that in. So let's solve for PV, okay? Now, PV is FV divided by this piece. Now, I don't like fractions. So a better way to do it, instead of dividing FV by this stuff, you could multiply by this by changing the sign of the exponents, as you know from a basic algebra course. So 1 over 2 cubed is the same thing as 1 times 2 to the negative 3. Conversely, 1 over 2 to the negative 3 is the same thing as 1 times 2 cubed. So if you don't like fractions, if you don't like to divide by this, FV divided by this, you could just multiply by the same thing, but just change the sign of the exponents. The same thing goes here. PV is FV divided by this, or PV equals FV times this with a negative sign in front of the exponents. So now, how do we solve for time? Let's say you tripled your money from $1,000 to $3,000, and your rate of return is 7%, and you were compounding annually, and you want to know how long it's going to take you to triple your money. In other words, we need to solve for t. Okay, so the first thing we always do is divide by PV both sides. That is the first. You've got to clean up the mess. It's got to have to look like this. Now, notice t is in the exponents. And the only way you're going to solve for t when it is in the air, in the exponents, you've got to introduce log function. I chose natural log on both sides instead of log, log base whatever, because it's just nicer. Feel free to use any log base anything. All right. Why do we choose log? Because one of the properties of logs is you can take this and move it to the left. And that's what I did here. Okay. Now I can solve for t. I can just say this divided by n times that. I did it in two pieces. I divided by this first. So nt is just this divided by that. Here it is. I know it looks ugly, but who cares? I'm trying to solve for t. And then to solve for t here, remove the n down, and here it is, done. Okay? The continuous case, it's actually nicer. Divide by PV both sides first. Introduce natural log. Natural log here makes more sense because the base here is e. Move the RT to the left, as you know, from one of the properties of logs. Natural log of e is 1. I hope you know that. That leaves me with RT. RT equals this. And then divide both sides by R, and you get T equals this. Looks a little nicer than this one. Okay. Finally, oh, let me say something about introducing log on both sides. I think it's important. So if somebody says to you, x equals y, do you have the right to say f of x equals f of y? The answer is yes. So if x equals y, then x squared equals y squared. Natural log of x equals natural log of y. E to the x equals e to the y. Square root of x equals square root of y. You can introduce any function you want. It has to be the same function though, okay? By the way, the converse is not true. So if f of x equals f of y, it does not mean x must be y. Okay, this is false. It can be true, but it doesn't have to be true. It does work when f is one-to-one function. We call them one-to-one function. If like logs, if log of x equals log of y, you have the right to say that x equals y. But if x squared equals y squared, you don't have the right to say this at all. Okay. In fact, you know the answer, right? So be careful. You have the right to introduce a function on both sides, but you don't have the right to remove the function on both sides because the inverse has to be, the function and its inverse have to be one-to-one. So that's a separate discussion anyway. So let's finish with, how do you solve for the rate of return? Imagine I want to triple my money from 1,000 to 3,000. I'm compounding annually, let's say. My time is 10 years. I'm curious. I want to know, what is my rate of return? Is it 16%? Is it 5%? You know, how am I doing, right? So we need to solve for R. Now notice R is on the floor. It's not in the exponents. So you don't want to think of log here, okay? In fact, if you use log, you're going to trap R even more. So you don't want to use log. The trick I'm going to use to get rid of this nt, I really need to get rid of nt because I'm trying to solve for R. This is not hard to remove. This is a little harder to remove. The first thing you need to do is move the PV again. Here it is. Then raise both sides to 1 over nt. And I did it in red. Why is this true? Why did I do this? Because you know that if a to the n to the power of m is the same thing as a to the n times m. As a side note, by the way, it is also a to m times n because multiplication is commutative, which is also this, right? Which means you can interchange these. This has nothing to do with the course, by the way, but just a side note. That's really cool because let's say somebody gives you this, right? Most kids will just say, oh, it's, I don't know what to do. Well, you can flip-flop them, can't you? You can flip-flop these. Now, you know cubic root of 8 is 2, and 2 to the 4 is 16. See how nice? Anyway, that's a side note. What I care about is this. I can multiply, okay? So let's go back here. Let's go back here. I'm going to multiply these. They cancel. You end up with this nice thing. And then I'm going to move. Do not multiply by n yet. So you got to move the 1 first, and then multiply everything by n. See? N is outside the brackets, and you're done. It looks ugly, but who cares? You were able to solve for R. For the continuous case, it is way much nicer. Notice R is in the exponents, just like t. which means we have to use logs. But I just did that here. To solve for r or to solve for t is the same process. That t goes here and that r goes here. So I'm not going to waste your time. It's the same thing I just did. Okay? So t was here and r was here. Okay? Again, I used log because r is in the exponent. In here, r is not in the exponent, so I had to use this trick. All right? Short and sweet. I will see you next time.